Hi everyone, welcome to another episode of the Common Lisp Study Group. I'm your host Ron Vadum with Atlanta Functional Programming. Today we're going to be completing our exploration of the very nice Lisp Interface Library created by Fari. Specifically today we're going to kind of tie up some loose ends that we've encountered over the last few weeks. Well, hopefully tie up some loose ends that we covered the last few weeks, and cover some of the available monadic transformations that are available in the library. I will first obviously introduce those of you who aren't familiar with monads to my understanding how monads work, so take some of which, if there are some corrections I have to make, those of you who have more knowledge of monads and how some of those work conceptually, please go ahead and post things into the YouTube comments, and I will make a follow-up video, covering some of that errata. As usual, those of you who like our videos, it would be appreciated if you go ahead and like the videos on YouTube, so that way more folks can actually see those videos pop up in the search results more quickly. Additionally, if you're on the YouTube live stream and you want to join us weekly, you could go ahead and subscribe to the Atlanta Functional Programming YouTube channel, and anytime a new video comes up, whether it be Common Lisp related, Haskell related, or anything FP related, you will certainly get updates from YouTube accordingly. A couple of announcements. Just as normal, Atlanta Functional Programming is looking for speakers to start off our monthly talk series. If you have a topic, functional programming related, in any language, whether it be, it doesn't have to be Lisp or Clojure or Scheme or Haskell or OCaml or anything like that. If you're interested in any FP related topic and you want to give a talk on it, please let me know. I'm available on Functional Programming Slack as Bugroom, as well as a Lisp Discord server as well. I'm also available on Tech 404 for those of you who are on the Tech 404 Slack channels. I usually am squatting in there just to talk to people and get some debugging information, stuff like that. So last time we kind of covered one of the final topics available in the Lisp Interface Library, specifically this sort of notion of what the author calls interface transformations, where he was trying to switch between a pure functional-based style into a temporary stateful style and back and forth. The transformation from the pure to stateful, of course, as I mentioned last time, is called the mutating interface. When you're doing stateful to pure, it's called a linearized interface. There are many examples that are already available in the library. But I thought in order to really drive the idea home, it might be a good idea to go ahead and implement one. So today we're going to be doing something like that in the live coding session. Additionally, we will spend some time also covering the monadic transformations. I'm going to start with the monads just because I'm not going to cover too much about how to actually implement your own monads. Just cover some of the related monads that are available in the library. That way, for those of you who are comfortable with monadic transformations, you can go ahead and start using them right away. This way, I haven't actually missed that specific topic, and then we can get into a live coding session of writing our own interface transformations for the rest of the time. 1 second here. I'm just noticing some lag. Also, as usual, for those of you who are on the live stream, if you have any questions at any point in time, feel free to go ahead and post them in the chat forums, and I will address them accordingly. Okay, so let's begin with our discussion of, we first load our project so that we have, which I think I loaded earlier, but okay. Now, as I mentioned, I think a few times in past episodes regarding monads in Lisp Interface Library, the little monads implementations kind of were, well, not kind of, they were heavily inspired by the Haskell equivalents. But I'm kind of, jumping ahead. Let me take a few steps back and kind of give a overview of what is an actual monad. I'm not going to get too much into the details of the category theory kind of like specifics in the formal definition, but in a nutshell, a monad is this ability for you to take in a transformation, okay, and be able to do some additional work within that transformation, and then be able to output it, and they all stay within the same container. The monad actually is itself could be viewed as a container type because internally it is keeping track of a specific state, and that is the value or set of values that you initially use to construct the monad. There are a couple of specific rules related to monads, specifically related to identity and the bind operator. One of which is obviously if you construct a monad with the identity in itself, it's as if you constructed it by skipping a step. I'm just trying to figure out the best way to write this down here, but it is just look up this specific thing here. It was right. So let's say you have. There we go. Just move this over here. Get this much better. Okay. So let's say you have a function, all right, that takes a type. I'm using some mathematical notation here just to illustrate the point here. So don't worry about this when we come into concrete examples, but this is the easiest way for me to kind of bring up this notion. Okay, so let's say you have a function that takes in a type of t1, okay, and it returns a monad, okay, of type t2, all right, and then the idea is if you wrap a value into a monad and bind it to this function, okay, it's the same as calling the function on the argument. So let's say that you have a function, this function here, and you have a type, let's call it a, which is of t1, okay, a value a of type t1, okay. If you have essentially a way to construct monads, okay, and you have this is one of the main things that you need to think about kind of construction. And it's just like a normal, you could think of it like a normal object constructor for now, but obviously there's some rules around how to construct it. But it's for the sake of conversation, we can keep it simple. Then, if you have this thing called the bind operator, if you do bind, and we call this function that constructs our monad, and we pass in this f, then one rule is that it's the same as applying f to this argument, okay? Now, obviously, that's a little convoluted for folks who are coming in from more eagerly evaluated environments. But there's a reason why this is kind of set up this way, and mainly it allows us to compose a series of transformations within this world of the monad, and then we can then return a much consistent representation of everything being of the same type in the same container. An example of this actually can occur when you start using in other languages optionals, and I've encountered this several times actually when coding in like say Java using Java streams, where you end up getting what's it a filter function that generates optionals, a series of optionals, and then you end up passing that into a map, and that itself also returns an optional. The mapping function returns an optional, so you get an optional of optionals. Obviously, that's going to become very convoluted over time. What you ultimately want is kind of a single optional value that tells you whether or not your transform value exists or not, right? So in those languages, what they did is they took these rules that I'm showing you here, and they've basically addressed them with patterns. So like if you have this optional optionals, then what should you do? You should normally do like a flat map, and this is a common technique even in Haskell that will take your collections and flattens them into the outermost collection type that you have. So if it starts off with say a list of lists, then it will only become a single list, which means it flattened all those lists that are members of the list of lists. Another rule, just to kind of bring this into identity, is if you try to bind any monad, any value, sorry, with the construct itself, which constructs the monad, it's the same. You're going to get the same value back. Okay, you're going to get the same monadic value back. Okay, so M is a monadic value. Construct will construct a monadic value, and then you'll get the same monadic value back. This is kind of like your identity operation here. The final thing about monads that really needs to kind of give you some of the values is something related to composition of functions. In math, a very important thing about a function composition is that ordering of the associativity should be preserved. Okay, and this can be best illustrated if I write this in Haskell-like syntax. But the idea is if you have a bind operator, okay, and you're binding an existing value that that was applied to a function f, and you're binding that monadic value to a function g, this is the same as essentially binding the monadic value to the composition using Haskell notation. Dot means composition, so f dot g, okay, which literally is the same as I'm sorry, I'm going to use equals here. Equals is assignment in a lot of cases for most folks, and this is the same as essentially taking f and applying it to essentially a lambda function that takes x and then binds that to binds the application of that to f of x with the value g. Okay, so this is kind of the equivalent of what we're looking at. Again, I apologize for the use of Haskell syntax on this, but it requires a little bit more typing to actually get it in Lisp. A little specifically, not the lambda necessarily, but the definition of bind needs to be, and the definition of compose need to actually be available for you. Now, luckily, for those of you who are wondering if Some of this is available for you. Composition, if I remember, is available. You could write function composition very quickly using, I think Alexandria implements the Gram implementation of compose. Compose, for those of you who are wondering what I mean by the Gram implementation, Paul Graham in his book on Lisp in chapter 4 actually wrote a very nice implementation of compose, where you could take a series of composition operators, and since we have essentially the ability to uh, uh, take variadic arguments using REST, it takes all the lists of functions that you pass in and using a REST argument, that becomes a collection, and then he wrote a very nice, very basic reduction that's available. I mean, I defer to you. I think we covered this in one of our earlier episodes on Lisp, but and I defer to our earlier episodes on when we covered some of that stuff on functional programming for more information. But the idea is basically it's a reduction of all the functions that were passed in a right to left associativity manner. So it's to preserve the mathematics, the mathematical composition definition of what function composition is. So what does all of this have to do with Lil? Well, we just simply do an apropos. I'm just going to go in and expand my REPL here a little bit on this, and then type in monad. Oops, sorry, I typed in apropos wrong. We will see that Lil actually provides quite a few different monads for us. It provides the identity monad. It has its own definition of identity monad, own definition of the list monad, the maybe monad, the state monad, and a couple of transformers specifically to maybe and lists, as well as some stuff about defining things like monadic functions versus monadic values. And some of these implementations that you see here with the colon are basically implementation types that you shouldn't actually try using in production code because those aren't actually exported symbols. Another review, I know I've said this multiple times, try to prefer not using colon symbols and try to use the exported interface. Those are the symbols that are defined in this section here in a package. For folks coming in and wondering what this is, this UIOP define package, I covered this before in our UIOP series, but in a nutshell, it's the equivalent of def package. The only difference is it adds a couple of features related to hot reloading and stuff that might be useful for you when you're specifically when you're defining more and more production value based Lisp libraries. I know a lot of libraries now have opted to using define package, and I'm just kind of following suit in terms of using it as well. Now, to use the monads, I hate to say this, but this is based on my discovery. There isn't quite a lot of documentation on how to leverage these monads in code. So I've been trying to play around with a couple of them, and we're going to do some of this live just so that it's easier to see what kind of mistakes you can encounter when you're dealing with some of this. The best way to actually start out on this is to simply look up the code for how the monads were implementation to see the interface values. Additionally, you could also always do something like a describe. So like, for example, let's take the simplest monad, which is usually the identity monad. That just usually echoes the monadic values that are passed in. Then we could just go lil interface monad identity. What? Oh, sorry. I think it's monad slash identity. And we will see that this here is your interface. It takes in the lambda list of arguments and derived types, and it tells you that the meta class is going to be identity monad. The result function, and it even tells you in its documentation that the result function for identity is clearly like CL identity. It simply returns the value passed to it. The bind function takes a monadic value, which in this case is identity of anything, and a monadic function, which is a one-argument function, and it just calls the function with a value and returns a result. So let's try some of this here. In order to do this, we've got to go into this and try. Nope. Before I actually try this, because I'm not entirely sure if identity itself was an abstract class in the monadic interface, it might be easier to first go into the code. And we can see that identity is a singleton interface, so we can actually construct it. And we can also see that it implements the methods here. So let's see if this works. So we do result, and then we just say our interface here, which is identity : identity, and then we just say 5, and you'll see that we're getting 5. And this is just the same thing as if we call identity of 5. Okay. But this is, this value returning isn't anything particularly interesting. The one thing that we should check is the check between the monadic function and the monadic value. So how do we define a monadic function? Because again, this is a monadic function on the identity. A monadic function is nothing more than a function that takes in a monad and returns a monad. Okay, and what it does is, you could think of this like boxing and unboxing. The monadic value is passed into the monadic function, which unboxes the value, applies the function to the value, and then it creates a new monad that, upon return, which contains the result value. Okay, so it's boxing that value into a monad, monadic construction. Okay. Those of you who are part, has a little plug for my other study group. Those of you who are part of the Haskell study group, we will be covering some of this this a little bit more in detail in that conceptually, just because there's more support for monads in Haskell than and Lisp Interface Libraries heavily inspired by that. So we'll be covering a lot of these details on monads in that specific study group. So my apologies for folks in this one, just because this library has its own kind of opinion on how some of this stuff works, but I don't know how much it fits into that realm, and we have to go into the conceptual realm in there to actually really cover that. So let's talk about binding. And if I do this, takes a value which is among. Okay, so let me see what happens if I do bind. Takes the monad, interface monad, identity, takes a monadic value, which let me just get rid of this window for right now, which in the case of identity is anything. So 5 is technically a monadic value. And a monadic function, which is just a function that takes one argument. So let's say that you get lambda x and multiplies times 2x. And let's see what happens here. And it returns the result. The result is okay. The result is the identity of the monadic value that's being passed in. So this is actually doing the right thing. So in the case of identity, and again, this is a very simple monad to get to wrap your head around. It's taking a monadic value, which really is, you could think of 5 being boxed in a monad of identity 5, because then it's that is what it is, right? The result of identity 5 is 5. So there's no reason to necessarily box it in the case of this design. But in a lot of other languages, particularly in Haskell, and I think you can implement it kind of similarly if you try to use monad as a pattern in some of the ML variants. 5 will be basically constructed as a before it's passed into this kind of function with bind. What it would do is it would do what's called a type construction, construct a new instance of that type with 5 wrapped around it. So then it becomes identity 5, and then we'd go ahead and apply this to this other function, which then internally will go unwrap it, apply the function, and then return a new instance of that identity monad with 10 wrapped into it. And the only way to get to the actual value 10 is by actually going ahead and doing result or some equivalent in that language to actually go and unwrap the value from the monad. Any questions on this? Bind and result is going to becomes more and more complicated when you start using out of the other monads that are available in the library, such as list, maybe, or even continuation. Continuation, my suspicion is continuation may not actually be complete, but I haven't actually tried it out, just mainly because I've heard that some parts of the parallel constructs and concurrent constructs in the library are incomplete. But I don't know if that's the case. But I'm giving you fair warning that you might see some of the monads and monadic transformations being in there not as complete as they should be, at least with respect to the semantics of Haskell. So let's go back to the list here. So we have the state monad, we have the inner monad, the monadic value. So one final note that I'm just going to mention on this one thing is the monadic transformers. I'll be honest with you, I'm not as familiar with the idea of it, so I'd rather not make the mistake of miscommunicating how this piece works. I may at a later time create a quick video for this one, but right now these transformers essentially, I think, follow the monadic transformers that's available in Haskell. So if you want to understand some of that stuff, I defer to how it's implemented in Haskell and then come back to this particular thing. But it just maintains kind of like these transformation pipelines that you can actually create. It's part of the compositionality of monads. These monadic transformers is as I understand it right now. I can't really say much more than that. Additionally, in terms of other monads that you may have read, okay, that are in the core Haskell library, they don't exist in here. Some of them are related to, I think, they're not even so much monads, like functors and applicatives. Those are, which are often used with these monads. They don't actually exist in this particular piece of the library. but I think the author's design is flexible enough that you can actually simply add it to it, and pull requests are welcome to add it to the library. And I'm sure the author will be enthusiastic to see some of those additions. Okay, so that's all I had really with monads, just because, like I said, some of these that are in various stages of maturity, and identity I've seen in enough places that I was able to actually play around with it pretty quickly. But with list, I haven't actually tried. Well, let's end it. Before we get into the final piece, since that's going to be more live coding, let me do one more example with the list one. This is all live here. I haven't actually played around with the list monad, but let's see how far I can get without making mistakes. Okay, so obviously, let me pull up just like this. Let's go ahead and get the list one. Okay. So here, if I'm understanding the list monad here, it's going to construct, it's going to take a value and create a list of one value, and then for the bind function, it's going to take monadic values, which is going to be probably your list of values, and then a monadic function, and then it's just going to simply apply the results and create a new function. It's going to essentially do a map. Although I don't know why this individual wrote func call mfv instead of just simply applying just doing a map car. But we'll see why. There might be a reason for that. For folks who aren't familiar with the loop syntax, append basically starts with an empty list and then just simply appends the results. You don't necessarily have to do like, start with create an empty list and then just doing like a push. That's unnecessary. Additionally, you could have also used collect, but I don't know why he didn't use that. So let's start with the first thing, result. If we just pass in our lucky 5, it's going to give us this error. What is this error? Oops, sorry, I forgot to pass in the interface. Okay. This guy is going to take a little interface monad list, and then 5, and then we see that it gets a list of 5. Think of this result right now with a single value as the construct that I brought up in our rules. Okay, this construct is what essentially what result is, right, in this interface. Go back. What the hell? Okay, so we have 5, and then if we do interface monad bind, and then we do list interface monad list, and then we provide a list of values. Okay, and then we provide a monadic function, which is a function of one argument. We're just doubling up just like before. If we return, okay, something here. 2 is not of type. Is not of. Oh, got it. I'm dumb. I have to return up. This function here has to be not just this. It has to be a list. So the reason for this monadic function is remember what a monadic function is. It takes in a value and returns it takes in a monadic value and returns a monadic value. Well, in the list case, that means it takes in a list and it returns a list. And internally, what this function is doing behind the scenes is it's actually taking in each of these values because it's unwrapping this Lisp monad, okay? And it's passing each of them one at a time, and it creates a list of lists that then gets flattened at the very end, okay? So the execution of this is basically the first iteration is it takes one, returns list with a single element of the times 2 applied to the value, so it returns a list of 2 with a single element of 2, then 4, then 6, then 8. So at the end of, before it returns everything, you will start with a list of lists like this: 6, 8, 10. Okay. But then what it does is internally it will actually and that might be the reason why he's using the append. It unwraps each one of these values and then constructs a final list. This is called a join if you look in some languages. It flattens that transformation and constructs one uber container type which has every transformed value. Okay, so that's the flattening part, the joining part of the operation. You don't see that here in this return value because it's already been done for you internally in the bind function itself. Okay. In fact, I'm wondering if I could just do, that's a method here, so I don't believe this is a, this will macro expand, but let me see if I can macro expand this one. Okay, this is just define interface method. That means I can't actually go and macro expand this one. Okay, that's fine. Okay, all right. Now, I encourage you to play around with a couple of the other monads that are available in the library, like the maybe monad, the state monad, and the continuation monad. But I'm going to just leave this list monad one up at here. And I mean, identity and list are the two most common ones that you would use if you're doing just collection-based transformations. State is another one that you use a lot in Haskell for various things, particularly I think IO is somehow related to the state monad too as well, but I don't know how. I don't remember how. I heard that it is. The maybe monad, maybe is Haskell's optional, so it's either this or nothing. Actually, I think either is optional. Maybe is no. Maybe is either or nothing. So it is. I'm pretty sure maybe is the optional type. And again, with maybe, then you get the same sort of ideas. I can quickly show you maybe too as well. Let's see if I can pull that up. Let's see. Maybe MT, maybe, yeah, maybe MT is what the important thing to think about. The main things about the maybe interface that's peculiar to its implementation to maintain the semantics, at least, of the maybe type itself, is some of these additional functions that might be unfamiliar to folks coming from Haskell looking at this library, and that is maybe or. He added a bunch of conditional logic that would do the same transformations while preserving the maybe type. So when you're constructing your algorithms that are using potentially the maybe monad, you have to use some of these logical operators that he provided in the interface in order for you to preserve the type when you're going through each of the individual transformations. And it allows you to also write stuff in an algebraic fashion too as well. So you can actually write a proper If you're using maybe or, it's going to be, I think, some types, and then maybe and is a product type. But I don't think maybe and is even available. I think maybe and is just subsumed by the fact that you could just create a maybe with the product type built into it. But some types are a little bit more difficult to actually handle. So, okay. So let's move on. Okay, so let's talk about making our own interface transformations. So there's a couple of things that we need to first do in order for us to illustrate this that I'm going to mention, and this is stuff that I've encountered when I was trying to grasp the mutating interface last week after our discussions, and it became apparent that in order to get started, at least with respect to our sequence interface needs to become abstract, and we need to create a pure version of this interface and then a stateful version of this interface. So what I'm going to first do in order for us to do that is a couple of things. One, I'm going to go ahead and I'm going to first make this sucker abstract. Okay, this itself is going to cause a lot of trouble because of the fact that all these other algorithms are kind of depending upon the fact that these are not abstract. So what I'm going to do is move these implementations to a singleton version of the pure interface, and then we'll write a stateful version, and then we can work from there to actually implement the mutating version and the linearized version of some of these functions. So this way you could then switch from a pure sequence to a stateful sequence, optimize for space and time, and then go back to a pure sequence if you ever wanted to, and then vice versa. So let's do that first. Let me... My apologies, I'm about to sneeze. Alright, sorry about that. Okay. 1 second. Let's make sure something's here. Okay, cool. Alright, so let's do this pure sequence. Actually, that this down a little bit so I can have a little bit more room to look at code. Then down here, let's pull up pure sequence. Okay, and what I'll do is first let's define our sequence. Right here. So now we have a pure sequence, and it's going to be our super interfaces. We'll have to include, obviously, well, we don't even have to do that. We just need to do AFP dot will dot tutorial sequence. And then this is going to be our singleton. And we have no parameterized types on this because there's nothing to parameterize on, really. So I think we could stick with the sequence monoid being the same because it's going to all, regardless of if you're going to be in a vector or a list, and whether you're stateful or not stateful, the monoid interface will be fine. Then the rest of these I have to go and bring down. I'm going to have to cut this and move this guy down here. There we go. And let's go to this guy here at the bottom. And let's do E, and we will change all these sequences to pure sequence. Done. Okay. So now we have our pure sequence version of this. And honestly, last time, I think I've mentioned this, the majority of these functions were already pure in the sense that they were using the common Lisp equivalents and the common Lisp sequence functions, the majority of them, unless you're using the N star versions like nconc or not nput or nreverse or push, not push new. You're not modifying the collection, you're actually sticking with creating a new instance of the sequence every time. So these should actually work. So let's see. I think the easiest way to do this is to restart my Lisp image and reload the project, just to clear out any sort of ambiguity in terms of symbols, and we can work from there. Okay, so let's restart. And sometimes you may want to do this when you're prototyping, occasionally restarting your Lisp image and then reconstructing the project. I know some folks like having long-running Lisp images. I tend to, if I'm especially doing heavily refactoring, I tend to restart my Lisp image 3 or 4 times just so that I don't have to deal with the painstaking process of uninterning everything and then reinterning stuff in the new packages that I've defined. I know other folks might have different opinions on this, but I'm just mentioning my process. Let's see if this does not complain. We're good. Let's see what it's complaining about. What is the... Got it. It's because of the fact that I'm defining something before in the sequence. So my apologies for that. That's an ASD issue. I'm going to pull up the ASD. This has to happen before or after this guy. Okay, let me restart this guy one more time. Okay. Should not throw anything, but we'll see. Class not found. What class is not found? There is no class CL pure : monoid. Ah, yes, that's right. One of the costs of, forgot that I had that in there. In the monoid functions, these two have to be defined as, this is wrong. This should be this, and the other one should also be this, because we're binding the sequence monoid to monoid. Yeah, okay. There we go. And one more time, just to be really safe about this, that I didn't do anything stupid. I'm just gonna go and restart and do it one more time, and then we'll be good. Okay. Good. All right. So now, MRS to switch over to pure. Let's see what happens when I do monoid fold star. All right, I'm already in the pure function, so I can just say pure sequence. Then the monoid is going to be just what I had before, tutorial sequence monoid. Foldable is going to be a list, 1, 2, 3, 4, 5. The function is going to be plus. Sequence is unbound. What sequence is unbound? One of these functions is defined as a. Oh, got it. I do have to move that other one. So one thing that I forgot that makes this all the mute is the group ID here. This is specialized on sequence, which is now an abstract class. It's no longer well, it's an abstract interface. It's no longer a singleton interface, right? And the cost of that is obviously now, even though we're going to have somewhat the same implementation of the sequence interface, because it's abstract, it can't be instantiated. It's not actually registered as a type in the little system, and so although the pure and stateful versions could technically share the same one, they can't anymore. At least based on this design. There might be a way of doing it by passing in the interface to a higher level function that would pass it in, but at this point your interface is basically already defined here by the pure sequence. And let me see here. Oh, right. p.will.tutorial. And which also means then we're going to have to actually. Okay, this is really going to become its own version. So I'm going to have to actually move pure sequence monoid here. My apologies, folks. This identity has to be preserved for all pure sequences. It's going to be different necessarily for stateful. So we're going to have to create a pure sequence monoid and a monoid for stateful sequences in order to keep them all isolated from each other. So let me go back to this, move this guy out. Oops. D4D. 4. Okay. Okay. %s sequence monoid with pure sequence monoid. Okay. And let's see here. Okay, go to monoid fold. Here. And that. So now we redefine this, which is saying that it can't find pure sequence monoid because I did not define it yet. I have to first define it, which means I have to define this guy, and now I can go and redefine these two. And this guy. Done. Okay. Okay. Hold on. Sequence font. Oh, right. Dummy. Now we got since we're passing this in, I have to change this guy. There we go. Now that works. Okay, cool. Not working. 16. No, that should be 15. Why is that saying 16? One. There's a bug in here. And that is in fold left. Yeah, this is the reason why. Because we've taken the first value, we can't actually use this. The first value has already been eaten. So the start is actually going to be 1, not necessarily n for fold left. Okay. There we go. That works. Which means I have to also fix fold right, because fold right is going to technically have the same problem when we eat stuff from the foldable. From end true, which means I have to provide let me start. Let me see what happens if I do this. Okay. And little interface fold right. Pure sequence. List 1, 2, 3, 4, 5. Add seed 1. Okay. If I do seed 0 though, it's going to be 14, which is wrong. Okay. I shouldn't actually modify these guys. It means that monoid fold, if empty, it should always provide the always provide 0 for right now, and then I'll go and figure out a way of providing empty for all types. The issue here is, just for folks who are wondering what the problem is in this debugging. I'm dealing right now with integers, okay, and even numbers. And for those who are familiar with this, the identity under addition for numbers is 0. Okay, that means is identity just basically means it's an element that if you apply any operation to any argument x, you'll get x back. Okay, so like in the case of addition, x plus 0 is obviously x. 0 plus x is obviously x, regardless of how it's applied. However, depending upon the type that's passed into the sequence, that identity may not necessarily be 0. It may be something else. So there's a way of you have to. I would have to use like maybe a type case to figure out what the different identities are and write out that implementation in empty correctly for all the basic types. But for right now, for simplicity's sake, I'm just going to go ahead and say Monadic fold is 0 here for both of these, just to maintain the correct functionality of the implementations, because then these are actually accurately defined, because the initial seed is the identity value, so you should actually get what you want here when you use Monadic fold, regardless of what you're passing in and so forth. Oops. Oopsie daisy. So it's also associated with the operator too, right? I forgot about that too. Damn it. Okay. I am going to ignore times for right now, and I'll fix out. I have to fix up. I literally have to fix up empty to actually to do the right thing for the sequence monoid. Okay, let's move on. So we have our implementation of the pure sequence minus a couple of issues that we've just encountered right now. We need to obviously create a version of the stateful of this. Well, the stateful of this is not necessarily going to be that much different. You may end up doing some optimizations like in fold left and fold right. But honestly, I think reduce is just fine in both the stateful and non-stateful case. The monoid fold and stuff in the stateful case, that's a little bit different. In fact, I'm wondering how they encountered that, they handled that in the map, because that is really one of the more complete versions of one of the more complete versions of this passing style already implemented. So if we go here and we look at pure, you'll see that they wrote all these different mix-ins, for example, for all the different types that you can actually go and deal with. Let me look at stateful. Yeah, .lisp. Yeah, there we go. And you'll see here in and of itself, I have to go look at the implementation. Okay. So map is an empty object. It'll go and check the key value for that. Decons, he goes and be able to modify the actual physical map and drop them. Update key is the same. It would require me to implement some of these more granular than what I currently have right now. We have a couple of things related to map2 and iterator. Okay, so he actually went and wrote a mixin for each type and then specialized it on that type. Okay. Yeah, he created all these different versions. And then that way you could just implement those mixins that are necessary in your singleton function. You'll get all those for free. So I'd have to implement a lot more in order for me to actually adopt this design, which is fine because that is kind of correct. You're maintaining the granularity. Okay, let's try that. Let's go back to pure sequence. Pure sequence itself isn't going to be dealing with any sort of types at all. And then I could do pure sequence of ints, which will handle all the different operators. But even there, identity becomes a real problem because it depends on whether we need additive identity or multiplicative identity. And those are two very different things. Multiplicative identity is 1. Additive identity is 0 when it comes to numbers. And in terms of matrices, what does it mean? Multiplicative identity is just the identity matrix for that. Additive identity, I think, is just a 0 matrix for yeah, it's just a 0 matrix. That's of the size of the actual matrix itself. Okay, this is going to be a little bit more complicated than I thought it would be when I understood this last night as I was going through it. But not too much. We could go with what we have right here. So we have this pure version. Let's go ahead and create the stateful version of this. Obviously, I'm going to have to create a new file. I'm going to address some of these other stuff. There's obviously some intricacies between the two implementations, and this is going to be really a copy paste exercise right now, just because I'm not fixing some of the things to adopt the design completely that the map implementation has, but it's going to get pretty close once we start refactoring it. But for now, we'll start with a pure clone of the pure sequence with some adjustments. Start this stateful sequence.lisp. Okay, and let me do this. Go here, pure. Let's go ahead and yank this entire thing, paste it, sync s, pure, stateful, and done. Okay, so we now have kind of a basic version of our stateful interfaces with everything kind of implemented the same way that we have before, because of the fact that right now we're not actually modifying things, but we could certainly fix some of this so that it is modifying things. Like, for example, instead of using reduce, we could write this to be a summation function. Using loop, at least, we could actually adopt loop to actually go and apply that. So let's see, how would we do that? We would can convert this guy to essentially something equivalent to like loop for for res equals seed for item in foldable actually do this for res equals seed, then I think that's correct. I'm sorry, that's not right. We need to actually apply the function first, and then we need to, it's not necessarily summing it. We need to actually apply the function to the current result and the seed result, starting with the seed. Let me think about that one and I'll write a newer version of this, and I can show you guys this. Reduce should be fine for now. Okay, so we now have a stateful version of this and a pure version of this, although right now they're identical. So you're not going to see much reasons for doing this, but can't find the package designator stateful. What are you talking about? Oh, now we're in stateful. Since we now have these two sequences, we can actually go into back and forth and actually implement a mutating version of this or a linearized version of this. Now, to reiterate what the linearized version is supposed to be, let me just pull up one thing here. This. Okay. So to create a pure version, a mutating version of an interface, we can go back to pure interfaces, and we can actually just simply do this. And I'm obviously not breaking this up into different different files, just for various reasons here. But really, it's just to kind of keep all this kind of connected together so that way when I check this in, you guys can have this. But to create this, there's a function called, essentially, if we remember, define, maybe it's in low core, define, not specialized functions, where is it? It is interface transformations. Transform. Where is apropos define. No, we could do mh who calls who references. Let me see if I could do this and describe define mutating interface. So this is a function that's in that's right. Lil transform mutating define mutating interface. This one is kind of what we saw before. It allows you to just define a version of the interface that we'll call, mutating sequence. Okay, and it takes a couple things. It takes like normal. It takes our super interfaces and our stateful interfaces. Okay, and they're separated. So the first thing that you need to obviously define here is our stateful interfaces, which we have in a separate package. We just do lil tutorial stateful interface. And now we need to provide our pure interfaces in the list of here. So here we have our pure interface already available. And then we have, do we have any slots? Are there any parametric stuff that we need to worry about? Not really here. So I'm just going to go whole list of stateful interfaces to mutate on. And I'm just going to go ahead and say list of pure interfaces. Mutate from. And let's see if I can get this. For some reason, this is not giving me. Everything is not properly indented for me, at least. Why is that happening? Okay. Let's see this. Let's do this. Add that. And do this. Okay, this looks a little bit better. Okay, so we have this, we have our things. We don't have any parameterized keys, but we want to actually make a parametric constructor that will take in an interface and then make the pure version or the stateful version. Actually, really, it's going to be the pure version, just because this mutating map is going to, at the end, construct this final, using this parametric function, this interface class. That's going to be the final result of our transformations. So this is all make. It's going to be in little core make interface, pure interface. And this is going to go ahead, figure out what our pure interfaces are, which is in this list, and then it will go and list those things to make the final interface instance. So this is done, I think. Let's see what it's complaining about. Compile with errors. Macro expansion. There is no class called stateful sequence. What? Did I not? One. Okay, I'm going to have to make a new file for this, it looks like. That way I can actually grab both of those. So, file, stateful, sequence, mutating sequence, and then file linearized sequence. Okay, so let's go and create our mutating sequence class. Source mutating sequence .lisp. This guy is going to be UIOP define package AFP little tutorial. Dot mutating UCL export mutating sequence. Okay, and this guy here, shift G, sorry. Okay, let's see if this changes. Oh yeah, go back to stateful, make sure I'm exporting this, which it looks like I am. Let's see here, stateful sequence is here. Looks like I'm gonna have to also do this for this too as well. AAP lil tutorial pure sequence. Let's see what happens. Still an error about no class. That's really weird because I could clearly see that it's there in the interface. What would be causing this issue? No class name AFP little tutorial stateful. I see that it's there. I see that I've exported it, so it should be available as a public symbol. Oh, wait a second. In package. This. Now let's try to do this again. This should have been. There seems to be something wrong with my exports that let me look at the macro expansion of this guy. Really? Okay, so it looks like it just doesn't see it. But I can see pure sequence. Since I created a new version of this, let's see this. ASP little stateful sequence. It's here. Oh, it says that it's an f-bound function. This might have been screwed up. Let me see if I can rectify this with the restart. This might complain, but we'll see. And it does. What is it complaining about? The true name. Oh, right. Let me just do one thing. I forgot about that. 10. Let me go ahead and create a new version, linearized sequence. And the linearized version is going to be the same as what we were doing before, but I'll go ahead and complete that for completeness sake before I post this. There we go. Just as I thought, looked like it was an issue with moving stuff around. My image got messed up. Let me go back to mutating sequence and show you this. Okay, so mutating sequence basically takes what our definition has, and it will go ahead and construct the mutating methods for you, I think. Or it's at the very least declaring them. And these are all the methods that are now a part of this interface that'll go and construct things. So once we do that, what does this do? So this creates a new interface class. It creates all the wrapper functions, actually, as you saw right there, for all the related methods, and it also declares the function to check between the pure and stateful packages to make sure that they have the same effects in the same model. Meaning, if there's a function that's in the pure sequence package, it should also be an equivalent one in the stateful package. That's what these guys here are doing. It's basically making sure that there's an alignment between the two specializations. That's one of the reasons why it's listed twice. A lot of these function declarations for each of these mutating functions here. The one thing that I think we have to do is implement specifically some of these more some of the more nuanced differences between the pure and stateful. We may have to go and actually implement the methods themselves, that is, especially ones that require an advanced kind of boxing, unboxing. And we covered this last week with looking at the map function. Essentially, this one is requiring us to actually go in and implement set box value in the case of the mutating interfaces. And obviously, for box construction, there is a function called box command to actually go and then create the box object for a given value. I will go and illustrate this with just a very simple example, just for one of these methods for completeness sake. But I won't cover all of the methods because, as you can see here, there's a lot of methods in the sequence interface and in general in the base library that you'd have to go and implement in order for your mutating interface to be properly preserved and leverage all the functions inside the system. You're essentially, what you're doing through this process, you're essentially extending the type system with an additional piece of semantics for your given interface types. So this way, if there are new variations of that interface, it doesn't necessarily have to go and reinvent the wheel, especially if the algorithms are all going to be the same for a given type, as we saw in the case of sequences. So let's do this very, very quickly for this one piece, just one method to simplify things. And that is, let's implement, let's say, lookup. Okay, it's probably the easiest way to interface that we can implement for this. And all this is doing is literally doing a def method, doing a little interface all lookup. Now this is obviously going to require you to actually, did I set this sequence up before? I may not have actually implemented this one for this guy. Let's not do lookup right now, because lookup, I think, requires me to actually hook up sequence to map, and I don't think I've actually done that conversion. I have to go look at some of the things related to hooking up things for other parts of the library. Let me try instead one of our favorable ones, which is, let's do fold left. Okay, this one is going to require us to do a foldable here. Obviously, our foldable is going to be our mutating sequence. Okay. Then all these other ones are going to be roughly the same. And what we're going to first do is we're going to first create a boxed value. Actually, you know what? This is actually a better one that will really illustrate this is insert. All insert. Where is insert? Maybe pure will have it. Let's try that. Pure. Interesting. It does not have that. Why is insert not showing? Sorry. Stateful. 1 second. Propose. Sorry. Stateful. Insert. Values. Interesting. Let me see something here. There we go. Where are you? Container, stateful, colon, insert. Nope. That's what I confused. Let me exit out of this one. Do def method will pure all. There we go. That's what I was looking for. And this guy will be going to use, oh, this is again requiring me to actually hook insert into sequence into a map. Okay, so I'm just going to have to do this way, then figure out how to add those functions. Okay, so with fold left, we've already talked about how quickly how simple this is to actually switch from to use a reduction to actually implement this. But really, what we'd want to do is we'd want to be able to first box the foldable object, then call fold left, then update the box with our results, and then reconstruct a pure version of this interface. Okay, so the way to do that is you need to first do lil/interface/all. I think it's called box. Yeah. And box is the type information. You need to first grab this. This will, and I think what I would have to first do is use a let star on this. Let, and then convert that into our boxed object, our boxed foldable. And now we have essentially a boxed version of this foldable object that we can now interact with. Okay. This is going to be used to keep track of the mutations, and once this is all good, we could then use And we'll, obviously um, modify this box using secBox value, which we'll use later on. And we could grab the pure version of this by using box value and it takes the value in the box as arguments and sets the box value. Just make sure that I do this right. Okay, so what we first do is, in order to make this all work, there's a couple things we need to first do. Let me change this and do a couple things first. First, we need to go grab a pure interface, okay, which we can encounter by just doing little interface all pure, or it would be why do I keep doing that? There. Pure interface. That's in little transform mutating, right? So this is little transform mutating pure interface. Foldable. This is going to grab the pure version of this interface, because that's how we're going to go and interact with the pure version of the sequence classes that we implemented. Okay. Then we need to go in and grab, because this is a mutating sequence already. So what's passed in here is of type mutating sequence. Okay. So because that's how the interface passing style works. You're actually adhering to the interface that you passed in as a first argument. So we need to actually grab the pure version first. So how do we do that? Well, that's simple. Box value will allow us to grab this. So we could actually go in and then do box pure sequence to being the little. One second, got to look at where box value is located. It was in interface box value, so I can actually use all, I think, to actually grab this. So all box value foldable, and this is going to give us the actual pure version of the sequence. Okay. Now everything actually is hooked up. Okay, we can now. Actually, there's one more thing we need to do. One is we need to take this pure sequence and we need to transform it into using our fold left, and we'll get a new version of that sequence. Okay. So this is going to be our result. Okay, and our result is going to hold. The call to fold left on our pure interface given our pure sequence and the function that we passed in and the seed. Okay. So now we have a transformed version of this using our pure API. Okay. But we didn't actually go in and adhere this to the box value, right? So in order to maintain that this is going to be a box value, we need to actually go and we need to update that value. And the way we do that is we create an updated map. So in order to do that, we'd have to use something called set box value. So set box value takes in two arguments: the new value, which we call res, and the object that we just got originally, which is in this case, it's called the foldable, okay, that we have passed in, because the foldable itself is of type mutating sequence. And what this is doing internally is it's going to take this result, this new sequence that we have, and literally just swap the value internally with this foldable sequence. So now when the mutating sequence is returned, if you want to actually look at the box value is going to actually be this result, okay? This is how you would actually implement, in a very simple fashion, a mutating method. It's just nothing more than an object override that takes in an object instance that adheres to the mutating interface that you're passing in as the first argument. And then you have access to the box API to actually go unbox the values and do whatever you need to do. The main thing that you want to know is if you have defined this parametric interface, you could use pure interface to actually go grab the pure version of what you defined in your defining mutating interface, and you can then use all the pure functions that we've already defined in the pure sequence API to actually go and implement your algorithms. And the one thing that you could do is after all these are all transformed, as you see in this simple let star, is you could just simply, before returning, set the box value of your passed in mutating instance with the result, and you can move on to the next version of the transformation, and everything is maintained. In this sense, you could think of this this interface transformation, especially the mutating transformations, has a form of a monadic transformation, although there are far more advanced versions of this. Now, I'm not going to go through all the implementations of all the fold left star, fold right star, because it's going to adopt the same pattern. But I think you could see that this is pretty simple to actually go in and actually implement a mutating version of this. Now, the linearized version of this is going to be the same idea. The only difference is instead of using boxed values, you have what are they called again? It was is it boxed? It's still boxed, but it's still it's called something else. The easiest way to do this is pull up the linearized version of the map that we saw the other day. Just without cluttering this up. It was in one second. Let me do something here. Linearized. Transform linearized map. Okay, that's probably the easiest way. Transform linearized map. Okay. So, yeah. Instead of using the box API that we were using, like box value, set box value, you want to use essentially one use value box, which is an explicit call to saying that if the one use value box essentially checks to see if there's an attempt to modify the same object twice, and if there is, it throws an exception. Like I said, I will go ahead and add a more complete example of this on our GitHub repository. But the idea is basically the same idea as what I showed you before with the pure sequence one. You're grabbing the linearized, the stateful version of the interface that you have once you define your your linearized interface. And then you need to go in and use one use value box to go and call the different stateful functions for your stateful interface once you've extracted it from the linearized interface. And once you're done with that, you could then make a function call to the pure interface constructor to actually go in and return a brand new instance of this object that's immutable. So it's the same idea. I encourage you to play around with some of those, but we will not cover that here. So with that, I've essentially covered the majority of what I wanted to cover for the Lisp Interface Library. I didn't cover every single bit and piece of the library, but I gave you kind of the basic design or overview of how everything works. Obviously, there's a lot more to this library than what I've covered in this stream, and AFP is more than willing to do more streams on this library if folks want. I, as usual, will post all the code examples that I have done today into our GitHub repository, and I'll post the GitHub URL as well in the announcements to folks who are on the meetup, folks who are on the stream. I will, I think I've already added the GitHub repository to this URL. If I've not, I will go ahead and post that into the YouTube description so that folks can have access to it. Are there questions? Okay, if there aren't any questions, I appreciate all of you for joining me today. I apologize for going a little over, but next week I'm planning on covering so there's a library that I've been playing around with that allows us to utilize Unix domain sockets actually through the Lisp REPL, which I was very excited about when I saw it. I'm still working through it. It's called CL Unix sockets, and I will show how to leverage that to interact with external programs through Unix sockets rather than file I/O. So with that, I will see you guys next week. Thanks.